Hi, I'm Matt Diederick, and I'm going to be presenting the paper Embedded Policing and Policy Enforcement Approach for Future Secure IoT Technologies, written by Zedekiah Hagen and Cesar of the Queen's University Belfast. The growing number of IoT devices, estimated to reach 20 billion in 2020, in an expanding range of domains from home to enterprise, has added new vulnerabilities for attackers to leverage. Current technologies such as hardware platform module and authentication mechanisms fail to completely protect against attacks and vulnerabilities. Security risk of IoT devices include user private data being compromise of industrial applications, corporate secrets being stolen, and hijacking of computing resources to launch attacks elsewhere. IoT devices are being exploited at a growing pace, with the security technology often being the exploited weakness. Their proposed solution. The paper introduces the idea of a security policy engine, a hardware-based software configurable solution that monitors activities on the communication bus, such as sensor and actuator control and access to peripherals. The proposed policing and policy enforcement approach uses the concept of policies to create a list of access control rules and actions to perform when a rule is violated. The proposed SPE solution is designed for resource-constrained devices and is a hardware system-on-chip component. It works alongside existing IoT security components to aid in providing a secure environment for IoT devices to operate. Central to our policy and policing and policy enforcement approach are the following hardware engines: a security policy engine, a security response engine, and an anti-tamper engine, which we will discuss later. The current IoT implementations include hardware and software solutions. The hardware solutions are Root of Trust, which uses a proof-of-knowledge approach based on challenge response protocol. Current standard is hardware Root of Trust and has the trust anchor banked into the device and generates a unique identity using the physical nature of the chip. Trusted computing gives users guarantees about expected behavior of the system and monitors for alteration from this baseline behavior. Trust zone-based integrity measurement architecture monitors the kernel to detect compromise and corruption from within the trust zone. Software solutions. The application sandbox is used by the Android OS to segregate applications in order to prevent outside access of data. Uses security-enhanced Linux to enforce the principle of least privilege by specifying minimal privileges and boundaries. Containers is a form of application isolation under the same kernel instance. The proposed system monitors system communication and behavior of the system resources and compares it to allowed behaviors for that resource. When an unexpected behavior occurs, for example, a malicious action from a compromised application, the system can take active and passive countermeasures to mitigate the attack and protect the system assets. Expected behavior shall be defined as the system security policy, which can be updated at any stage of the device lifecycle. The proposed policy and policing enforcement system architecture will not only enhance the security of the device, but will also improve its flexibility to meet changing security requirements of next generation embedded and IoT architectures, as well as the next generation of threats. The proposed architecture. The proposed architecture uses a Xilinx Zinc Ultra-Scale MP SoC. This platform is chosen due to the on-chip availability of hardware security and cryptographic features. The MP SoC features an on-chip quad-core ARM Cortex ece554 APU for general-purpose computing and a dual-core ARM Cortex R5 RPU for critical application applications requiring deterministic low latency. User software will execute on APUs and treat it as untrusted application. On the other hand, the application to configure and manage the critical components of our proposed system architecture will run on RPU and be treated as trusted applications. The RPU has a dual 64 kilobyte tightly coupled memory that is physically isolated from the APU and the L1 and L2 cache memory. The physical isolation and segregation ensure that untrusted applications cannot read, write, or modify any part of the tightly coupled RPU memory. To maximize flexibility to changes and security policies, each hardware engine has a AX14 Lite communication that can be used by the RPU to configure and program engine-specific security parameters. This can fulfill the proposed architecture to meet the dynamic security requirements of different devices. Here we can see the proposed system architecture, where the APU and the RPU are segregated from the components, and the security policy engine integrates with the peripherals such as the network and I/O and sensor devices before being input into the system. Then they output their response to the security response engine, which we will talk about soon. The security policy engine, the SPE, has implemented using FPGA GUI logic to monitor system-level communication among system peripherals and memory blocks, comparing against the defined policies for each resource, and initiates proactive response actions to counteract attacks. The SPE is comparable to a policy-based hardware firewall, which checks the approved list of devices and either grants or restricts access to the device. The SPE engine enforces system, resource, and specific requirements by actively monitoring shared communications at the interface between AMBA, AX14 bus, and target system resources such as memory, sensor, and actuator. The SPE itself is composed of an AX14 sniffer block, device table, policy table, decision block, and engine configuration block. The AX14 sniffer monitors and maintains the necessary AX14 handshake signals as defined in the ARM AMBA AX14 communication protocol specification until the decision block checks and grants access to the target resource. The device table contains a list of trusted requesting resources that are permitted to access the target resource. In this table, each trusted requesting resource has a corresponding base address of the security policies that specify the access rights linked to it. The policy table contains the permission rights of the target resource that corresponds to each trusted requesting resource. The stored policies can be simple as address, read, write permissions, or more complex policies. The decision block receives a program reference policy issued by the policy table, compares the status of AX14 signals as per security policy, and generates a result. The generated result will be passed to the AXI sniffer, which then either grants or blocks the requested AX14 transaction. The engine configuration block provides functionality to program and configure the security parameters of the SPE using a secure application running on the RPU via the AX14 Lite communication interface. Here we can see the layout of the security policy engine, where the AX14 sniffer is communicating with the device table and the policy table, then passing data to the decision block and outputs the response. The secure response engine and anti-tamper engine. The secure response engine provides effective active responses to security threats reported by the decision block. to initiate mitigation response. It does this by interrupting the secure code running on the RPU and requests the time-critical interrupt service. The proactive response will be initiated by executing the interrupt service routine of the SRE and is enforced by the anti-tamper engine. Examples of proactive responses are disabling system read, back interfaces, initiation of secure lockdown of the system resources, initiation of system reset. The anti-tamper engine enforces the proactive measures initiated by the SRE. It provides passive physical security measures against hardware-level attacks such as side channel analysis by monitoring the device's physical parameters such as voltage and temperature. It activates an alarm if the system violates the set condition. My thoughts and opinions on the paper. Overall, I believe the authors provide a very good paper and strong proof of concept for their policing and policy approach to embedded device security and elaborate on how it can strengthen the security of current and future IoT devices, but could also use further clarification in some areas. Though the authors make it clear they propose a solution to fill shortcomings in current security implementations, and they even outline the current standard security implementations. But they fail to outline where these practices fall short in providing a secure IoT environment and how their proposed solution will fill these shortcomings and how it will, as they state, complement existing security technologies and embedded architectures. Though a section of the paper was titled Vulnerabilities and Threats Posed to IoT Devices, and the authors describe many of the liabilities of these devices, but failed to mention how these proposed solutions resolve these weaknesses. The modulation of the system into separate engines allows the system designers to divide their responsibilities in an intelligent and organized manner and opens the system up for extension. The authors propose a system architecture that uses a Xilinx Zinc Alta-Scale MPSoC that contains an ARM AMBA X14 communication bus. While these outline solution is well thought out and feasible, the paper contains no mention of if the solution is dependent on this chip and bus type or if the system is extensible to run on various hardware platforms. The proposed platform is deemed to be configurable at PowerUp by programming the device with policies that are stored in the device's policy table. Further explanation of how the host, applications, and users will interface with the system to provide the policy information would further elaborate on the author's vision of system use and functionality. Conclusion. The integration of a software-defined and hardware-enforced security policy engine brings adaptability to security platforms, where the same platform can be used to fulfill the diverse security requirements of different application domains. The proposed system architecture complements state-of-the-art chain of trust and authentication mechanisms, which mitigates against existing vulnerabilities and attacks and provides robust security measures. Future hardware work will be focused on enabling secure configuration of system hardware components and policing of more complex communication attributes. From a software perspective, future work shall be targeted to provide isolation and segregation of hardware resources requested by software components while being managed by the operating system.